All right. Hello, this is our interim presentation for our project into redeveloping a cordless hand drill to be designed for manufacturing. So our initial proposal featured a different drill that we've since switched to a Black & Decker drill model with all the functional components included as our new baseline. Here you can kind of see a section view with all the colored components colored for differentiation, so you can kind of make out what's different and what's there in the motor, the gearbox. The basic idea behind the design is to power a motor that can reach high speeds using a gearbox to rotate a chuck that is capable of holding a tool, if you weren't already familiar with uh, household hand drills. With this exploded view, you can kind of see more of the inner workings, along with an itemized list on the side that has all the major components for this hand drill. And yes, the point of our project is to eventually redesign this for manufacturing.
The main primary industry that we see this being used in is the construction industry, where these tools would be used daily on the job site by all people there. And the secondary group that we see are DIYers or amateur builders who will use these tools much less frequency and with much less intensity than the primary group. We're estimating to produce about 10 million units per year. Moving into the product analysis for this device, starting with our fast breakdown, the primary goal is to rotate the tool, and we can do that by securing the tool and applying torque. And breaking down into just the other components of it, we can assure convenience, enhance the product, and please sensors by adding extra controls and softening the grip and just making the tool more ergonomic to use.
All right, so we now move forward to our assembly sequences for this hand drill. So for our first assembly sequence, we're going to start internally and build out. So we'll start with the motor and then attach the gearbox and direction switch, which are shown in our exploded CAD view. And then we'll attach our speed adjust assembly before attaching the chuck and trigger all inside. And then finally, we'll put on our body shell and then add in the battery assembly. And then we have an assembled drill for the sequence. All right, so for assembly sequence 2, we instead start externally and then work our way in. So we start with one of the body shells, then we put in our motor and gearbox. And once we have that assembly, we put in the direction switch, and then it's very similar to the first assembly sequence. We add our speed adjust assembly, our chuck assembly, and then we have our trigger before snapping in the other side of the body shell and adding in our assembly for the batteries. So once we compare these two directly to each other, we used 5 different criterion for judging these, and each sequence got a score between 1 and 3, with 1 being the worst and 3 being the best. So sequence 1 performed better in every criterion by 1 point, and that kind of makes sense. Since we wait till the end to put the housing over everything, it's a lot more easy to access all of our internal parts. So this helps us be able to test our sub-assemblies and assemble those sub-assemblies in parallel before actually putting everything together in the end. So overall, in the end, sequence 1 we've evaluated to be a much stronger assembly sequence for the drill.
All right, so moving forward, here's the functional component mapping matrix for the hand drill. So we've taken critical components of the drill and placed them on the vertical axis and the basic functions on the horizontal axis, and have marked which components fulfill which functions. This sort of just helps to visually map out the completion of each function. And as can be seen, the product is fairly modular since cross-functionality between components is minimal. So this offers good opportunity to produce a product family with common interfaces between parts. So moving forward here, here's the bill of materials for the product. This shows a breakdown of each individual component's manufacturing and assembly costs, as well as other specs such as materials, size, and manufacturing process. So if we look to the next slide, the remainder of the BOM can be seen, as well as a total product cost of about $28.48.
Moving on, using our bill of materials, we were able to classify the parts by their functional importance and cost. From this analysis, the parts that we recommend to redesign are the chuck, inner battery, drill axle, and chuck jaw piece, and then as the motor and gearbox and battery are pre-purchased, because these pieces have a high assembly cost and high functional importance. Using these functions from the FAST diagram, we're able to differentiate between our customers the important functions that differ for each other, and for, in this case, the different customers have different importances for controlling the torque. And this relates to the modules. The modules that relate to the function of controlling the torque include the torque ring and the plastic body.
So on the left, we have the CAD for the torque ring as it exists now. And for the mini drill, this part is eliminated as we expect the consumer to not be concerned with torque control. On the left here, we have the CAD for the left body shell as it exists in the normal drill. And in the normal drill, it'll remain unmodified. But with the mini drill, it'll have an extended extrusion to act as a body cover where the ring once was. The torque ring interfaces with the chuck and the gearbox in the normal drill. And without the torque ring, these two components won't interface directly. And the left body, the body shells will have the extra body cover. And here's our product family assembly diagram with the normal drill and the mini drill having mostly the same assembly process up until the drill axle. And then after that, the normal drill has the torque ring added, and then the drill chuck, and then the outer housing, while the mini drill just has the drill chuck and then the outer housing.